Hey everyone, thank you for the Professor Radical and the organizer let me here to report my recent work on the collective motion. In this talk, I will discuss the influence of time delay and noise on the collective motion of a self-propelled particle system. I'm Yongzheng Sun. I'm from China. First, I'll give some background of the collective animal behavior. Then we will discuss time-delayed SPP model. Finally, I will discuss the influence of noise on flocking of a stochastic Cuckoo-Snell model. Examples of collective motion include swarming locusts and fishing in school and flocking birds. This picture is taken from the Viscous review paper. In general, the collective motion is often modeled by the SPP model, which assumes that each individual adjusts its state according to the state of his neighbor. Among the most interesting aspects of collective motion is their sudden changes in direction. In 2006, Boer investigated the swarming of locusts. They put some locusts on a ring-shaped experiment arena, and they also established a SPP model to explain their experiment data. They found that the collective behavior of marching locusts mainly depend on the group size or group density. They found that at a low density, as shown in Figure A, the motion of the group has a low alignment. For intermediate density, all motion was interrupted by sudden change in direction from clockwise direction change to counterclockwise direction, and so on. But for high density, the changes in direction didn't take place. All locusts quickly adopt a persistent rotational direction. In general, the group level behavior can be described by the following Lagrangian equation, where Fu and Du are drift and diffusion coefficients. Boer's SPP model predicts that Du is independent of U. It's almost constant.
U is velocity?
Yeah, U is average velocity of the group.
So the drift is really like an acceleration?
It's a drift. This is drift. This is diffusion.
I'm just saying, in an abstract mathematical sense, that makes sense. But I'm just saying, from a more physical sense, right? If U is velocity and F is the average time derivative of that, isn't it telling you more about acceleration of the locusts than their drift?
Yeah, I want to say, but if the detailed analysis show that Du should have a quadratic shape. This quadratic shape means that Du has a local maximum around the U is 0, which means
the locust here?
Not single, it's a group. Yeah. It means that the group level fluctuation increase if the system is in the disorder state. If the disorder state means the U, the group average velocity is around 0. Sorry.
It's also different than the diffusion that one would normally talk about for particles, right?
Sorry?
I mean, normally you would think of diffusion as x of t plus delta t minus x of t divided by delta t, but here it's sort of like a diffusion of velocity, so to speak. So it's more kind of like a measure of noisiness of the acceleration, right?
Yeah. In order to make the experiment data better, and in 2009, established another SPP model. In this model, they introduce a non-trivial noise function, eta, and the eta is like this. Is as shown in equation 5, which means that each individual responds to the loss of its alignment by increasing its own fluctuation. And here, UIR is the local average velocity. And
max is max over what?
What?
When you say max of UIR, what are you maximizing?
Yeah, the maximum is the maximum velocity around the individual eye. This is, you mean this?
Oh, I see, it's a function. Okay, sorry.
Yeah. And the SPP model 3 to 5. If we calculate, we can find that the diffusion coefficient du in model 3 to 5 in this model has a quadric shape, which makes the experimental data well.
What is the meaning of having negative diffusion coefficient? Because you show in your model you have square root of du. Here, I mean, if I can read correctly, here you have 0, 0, minus 5. No, I'm sorry. This is 0. Okay, no, I'm sorry. Okay. No.
Okay. In the following, we will show that the time delay model can also explain the experimental data. In the time delay model, eta is constant, and the same with Bohr's model. We think that the interaction between individuals is not necessarily be instantaneous. There should be a time delay because there needs some time to translate the information or process the information. So we introduce time delay into this model. We will show that our time delay model can also explain the experimental data. According to Bohr's experiment arena, we consider a group of n individuals moving along a one-dimensional circle, which we identify with interval omega, and xi is individual's state position. Vi is velocity, and UIR is the average velocity of individuals which are within the R neighborhood of I's individual at time t. Firstly, we give the numerical result of the time delay model. We plot the average velocity u for the group as a function of time. We simulate the model with different time delay. At the beginning, we set time delay is 0. And after that, we set time delay is half. Finally, we set time delay is 1. From this figure, we can find that the mean switching time for the change in integration is increased as the time delay increase. We also investigate the influence of group size on the mean switching time. The result is plotted in figure B. We can see that the mean switching time is an increasing function of group size, and this blue circle is for the model without delay, and the red square is for the model with delay is half, and the green triangles is the result for the model with tau is 1. We can see that for the model without delay or with small delay or with large delay, the mean swing time is an increasing function of the group size. We can also find that for each group N, the group with large delay, the mean swing time for the group with large delay is longer than that of the model with small delay, which the influence of time delay is further illustrated in these two figures. In this figure, for the group size N is 20, we simulate the model with different time delay. We also simulate with the model with large delay, but if the delay is about 5.5 seconds and the changes in duration didn't take place. So in figure A, we only show the result for the delay between 0 to 3. This blue circle is for the time delay model, and this red squares is for our revised model. We will discuss it later. From this figure, we can see that the mean switching time is also an increasing function of time delay, which means that the group can keep all the motion by increasing their response time delay. To understand the mechanism under the generation of the collective motion, we analyze our model. Firstly, we analyze our model for large R and small tau. Since in this case we can give a theoretical result. For R is half, because we consider the system movable in the interval 1 to 0. So if R is half, this means that all individuals will interact each other. Then the local velocity average UIR in equation 7 is then equal to the global velocity U. So equation 7 reduced to equation 8, and then we adding all equation 8 for I and dividing it by n, we get the equation for the variable u. And we let PUT denote the probability density of the stochastic process defined by equation 9. Then equation 9 will satisfy the following delay for collecting equation. Let PST be the corresponding stationary distribution. Analyze PST is a valid method to understand the group level behavior. In the following, we're using the small delay approximation method, and we can get the PST, the first order approximation of PST, as shown you equation 10.
Sorry, so I'm not used to thinking about delayed stochastic equations. Is that delay Fokker-Planck equation, is that rigorous, or is that an approximation somehow?
This one.
Is there any approximation made in writing that down? Or is that exact? Because it's not a Markov process, right? So you have to generalize it somehow, and I don't know if is that the correct generalization?
This is based from our model equation 9.
And it's exact. That's my question.
Yeah. This is exact form. And we analyze this based on the small delay approximation method. This is the analytical result.
The small delay is almost like putting friction into the system, isn't it?
Sorry.
So if you go back to your stochastic equation, right, and imagine that we just did the small tau approximation here. Oh no, it's not friction because you have like strange terms.
So this is only for the large R and small tau.
And this next is for general R.
This is only for big R, large R.
I guess what I'm saying is it easier to understand what the small delay approximation is doing if you do it first on the SDE and then do the conversion to Fokker-Planck rather than do it on the Fokker-Planck equation? Okay, go ahead.
Sorry, because maybe
Sorry,
the
I talk fast. So I'm just wondering, sometimes when I see people do small delay approximations, it's a little bit easier to understand what's going on when that's done at the, even formally at the level of the stochastic equation, rather than once it's already in this kind of complicated PD framework. It's to me a little bit harder to see, what's going on.
Yeah, I understand.
Don't you have to? I mean, isn't this integral over R? Don't you need something over function space? Because in the delay case, you're basically talking about, or unless you're fixing an initial condition, but it's not really stated in your probability density here, right? I mean, there may be an implicit assumption of a particular initial condition, but otherwise you need the equation to be stated in that way.
Yeah,
for sure.
So, is there an implicit assumption about initial conditions here, or?
So we only assume that R is larger, then the local integration model will become to equation 9, and we analyze it. You mean we should put some assumption on the original model?
Well, whenever you have a delay like this, right, your initial condition is in function space, right? You're in infinite dimensions. So that needs to somehow be in the density. Although it could be exactly as Pete was saying, since you take a small delay approximation, you're going to use that anyway, then in some sense you could have just done that on the original equation and derived everything from there. And that also tends to limit the assumptions for initial conditions and things.
But I think you're right about the initial conditions, but I'm just thinking if you go back to the stochastic equation, you've got a discontinuous function of u, right? So with the small tau expansion, isn't that problematic in the sense how do you do like normally I'm used to seeing a Taylor expansion of, terms when you take small delay, but the sign can change by an order 1 amount when tau is small, right? Is that cause concern?
Yeah. Because I already based on this method. This method is I saw from the published paper in PRE, and they give the small delay approximation method.
So what was the reference you used for this?
Sorry, I missed it. It's about in 2006 in PRE
By?
published. Please, I'm sorry, I don't take my paper. Maybe you see my. You can find the reference from this paper. This will be this. You can find the reference.
Yeah.
And we just get the PST, the first order approximation of PST. And then we plot the PST with different delay. we can find that the PST has two maximum, and at u is minus 1 and u is 1. And the blue one is for toys 3 and green one is for toys 1. From this we can see that it is easy for one to distinguish two-step that for large toy. So this is consistent with our model. In order to analyze our full model in 6 to 7, in the following we use the equation-free method. And firstly, we assume that for the cost variable u, the behavior for the cost variable u, we have the following Langevin equation. And based on the equation-free method, we can get fu and du using the time series obtained by stochastic simulation of the model 6 to 7. Here, small delta t is a time scale which usually is several times of the simulation time steps. It's easy to see that the calculation of fu and du depends on delta t. We will show, or in order to show the choice of delta t is meaningful, we calculate PST using equation 13, and we also can get the PST by finding the time series from the simulation of the model. From this figure, the red one is the approximation of the stationary probability distribution using equation 13, and the blue one is the histogram we get by finding the experiment data. We can see that the match is excellent, and we can also calculate the diffusion coefficient du. From this figure, we can see that if we restrict the u between minus 1 to 1, and the du has approximately a quadratic shape, and u has and the du has a global maximum around u is 0, and it has a low it has a minimum, a local minimum at u is minus 1 and 1. This means that the noise regains its strength as the system leaves u is plus and minus 1, which helps the system to return to one of its favorable state.
So sorry, I forgot what the equation numbers are. So the model you're using is with the time delay, right? So this is like this interacting with our neighborhood, right?
Yeah.
Okay. And so the point is then you're doing the equation-free method, which doesn't have delay, right?
No, we use our equation-free method with delay, with small delay.
Okay, so what is the equation into which that you're calling your equation-free equation? I mean, the equation-free method says fit a drift coefficient, fit a diffusion coefficient. There it is. So where's the delay in that?
Yeah, this we call this for the cost variable u. We can.
Yeah, sorry. Can you go back to 6 and 7 again, just so we can see 6 and 7 again?
6, 7. Okay. This is our time delay model.
Right.
And this Vi is the velocity for each individual, and the big U, capital U, is for the global velocity, and we call it as here.
this equation-free method, there's no delay in that equation, is there?
Yeah, there's no delay. Yeah.
Okay, so my point is that somehow you're trying to shoehorn a model with delay into a model that doesn't have delay. And so what I'm guessing is happening is what you're seeing is that the fusion looks stronger when you're away from plus or minus 1 because the delayed drift term has some noise when you're away from plus or minus 1 that's more than when you happen to be close to plus or minus 1?
You are right. Maybe some I think this equation there are no delay, but we use this method and we support our model with delay. So you are right. Maybe we can. I can talk to you with how to explain this. Yeah. In the bow, we only consider the model with uniform delay, and the delay is the same for all individuals. In the following, we consider the time delay model with non-uniform delay. First, we consider the model with delay tau is a function of time t, as shown you in 16. In 16, we can see that where tau represents the information transmission delay in high local group alignment, and max Vg means max absolute value of the velocity. From equation, this equation, we can see that if the individual lost his alignment, and the tau I t will increase. We only do some simulation work on this model, and
sorry, the motivation for your time delay was that you want there to be a longer time delay when what happens?
Like delay?
You said something like when the swimmers lose their line or something,
yeah.
Then the time delay gets longer.
Yeah. From here, you can see that if the individual loses his alignment, it means the group movement is disordered. Then it will need a long time to recognize its neighbor's state. So the tau will increase because this is the max velocity of his neighbor, and this is the local average velocity. So if the system in low alignment, this will big.
So what made you not be happy with the uniform delay? Why is there some biological or observational reason that you wanted to make this generalization?
We make this assumption because we think just like we drive a car on the road, if the traffic is difficult, it will need much time to make decision. So
It's not like the traffic was coming the opposite direction, you would decide pretty quick.
Yeah. And we only do some numerical result for this model, and we compare the mean switching time for the original model and the revised model. The red one, the red squares is for the model with for the revised model. This blue circle is for the original time delay model. We can see that the mean switching time for the revised model is larger than that of the for the model with constant delay, which means that the group can keep automotion by increasing their delay. So we can conclude that time delay can can help the group to keep automotion. In our final example, we consider the model with random distribution delay, tau I. Here tau I is constant, but we consider tau I get from some random distribution. We consider two different distributions. First is exponential distribution. The other is normal distribution. We also do some simulation on this model, and we plot the mean switching time for the model with constant delay, the blue one, and for the model with exponential delay, the green one, and for the model with normal distribution, the about two is this one, the red one is for the model with normal distribution with C1, and the above one is for the model with distribution with C2. Okay. In the first part, we discussed the influence of time delay on the collector motion. In the second part, we consider the influence of noise on flocking of a stochastic Kuhn-Smart model. In general, there are two famous SPP models. One is Wiesek model. Wiesek model assumes that each individual adjusts their state according to its near neighbor's state, and there is a phase transition in Wiesek model, which depend on the group size. Different from Wiesek model, Kuhn-Smart model assume that all individuals interact each other, and the communication rate depends on the distance between two agents, and is a non-increasing function. Cook and Small in 2007 showed that there also is a phase transition which depends on the parameter beta. If beta is less than half, then the flocking will emerge. If beta is greater than half, and there is also flocking, but we need to give some limit on the initial state. We assume that in noisy environment, we assume that there are measurement error, and this measurement error is proportional to the difference of velocity, and we replace Vg with Yij. Then we can get a stochastic Kuhn-Smart model, as shown in equation 20. The question is how to get high convergence rate. The results for the Wiesek model show that we can improve the convergence speed by optimizing the communication rate, or by designing the optimal graph topology, or by using the finite time control method. But for the stochastic Kuhn-Smart model, because all individuals are interact each other, so it's better to use the finite time control method. So we input a term to the model equation 20, and we have this stochastic Kuhn-Smart type model. We say system 21 reach stochastic flocking in finite time if the difference of velocity tends to 0 in finite time, and the diameter of the group is bounded in mean square. Here T1 is called the converging time.
Sorry, where's the control?
The control here is showing this term. This term is we add to the equation 20. This is a stochastic CS model in order to get.
What function is being controlled? I mean, that just depends on v's. I thought the v's are just variables that evolve according to physical laws. Are we thinking about control like someone's trying to control the flocking to get it to get the consensus?
Here we mean control. Control means add some term to the function, and we means control. Maybe this control is different from the physical control. Yeah.
So, but in other words, there's no tuning this control. You just put it in.
Yeah. You're right. Yeah.
It's just a nonlinearity, right?
Yeah. This.
So it's just adding a nonlinearity to somehow
The size is already
change the
nonlinear.
behavior.
This is non-linear because for the linear system, the system will converge in. Based on the stability theory for SDE, we have this proposition, and we show that if the communication rate has a low bound psi star, and if the sigma means the strength of noise, is less than the square root of psi star, then the individuals in system 21 can reach the stochastic flocking in finite time. And for the convergence time T1, we have the estimation as shown in 22. And here we only show the numerical result for the model with constant communication rate. We also do some simulation for other communication rate. If we use psi is 1, then we can see that the psi star is 1, and the upper bound for the noise strength is sigma c is also 1. So we use two flocking indicators, delta x and delta v. And the other parameters is shown here. We can, from these two figures, we can see that the system reach flocking in finite time. And we also investigate the influence of noise on the converging time. Because the sigma c, sigma c for for psi s is 1, here is 1. So we firstly simulate the model with when sigma is between 0 to 1, and we get the converging time directly from the simulation, and we can find that the converging time decrease when sigma increase. And we also do simulation with large sigma. We can see that for high level of noise, the converging time will increase. And if the noise is too large, there will no flocking. These two figures show that suitable noise can accelerate the emergence of flocking. We also investigate the influence of group size on the converging time. Both our theoretical and numerical results uncover parallel relationship between the converging time and the number of individuals, which means that it is easy for the group with a large size to reach the flocking. Okay, here is a summary. From this talk, we can know that time delay has an important influence on the group level dynamics of the SPP systems, and a rapid transition occurs from this order moment to highly aligned collective motion as the density of group or the time delay increase. We can also see that suitable noise can accelerate the emergence of locking. And I will thank my collaborator, Prof. and Professor Wei and Dr. Jin. Thank you for your attention. 谢谢大家。
So if I understand the logic of this control, if there were just two animals, whatever, and then I guess what's happening is under the normal cook or smell, once they get close enough, it's sort of like the velocities will converge at some exponential rate, right? And what you're doing, instead of having an equation with like dz equals minus c times z, which is exponential decay, you make it z to a power less than 1 to kind of make it kind of collide to 0 in finite time, right?
Yeah.
That's, I guess, what the logic is. But then I guess in practice, though, would that be sort of more susceptible to instabilities because somehow you're kind of making the dependence on the velocity non-smooth as it gets closer?
Yeah, you're right. Yeah, it means this is term. So how to improve?
Alpha's less than 1, right?
Yeah, where?
Alpha, your exponent, I assume it's less than 1 on your control.
Control, yeah.
Alpha.
Alpha.
Is that assumed less than 1?
No. We assume that it's a small number between 0 to 1.
Yeah.
Between 0 to 1.
So, actually, have an offer for you. Wait. If you think, I spent the last couple of years actually in Veto labs to look at sperm motion in very fancy places, such as the uterus.
Which
And
university?
what?
Which university?
In Paris. We have all kind of facilities to have fun. It's pornography for animals. But behind we have
There's no pornography.
a goal. I'm sorry?
But there's no pornography.
Sure. That's what I'm saying. Let's say it's entertainment for scientists. Let's put it in this way. So my question is this. Now, I mean, you know that there's a problem of fertility which has to do with micro swimmers that are moving. And still, you know, we don't understand how they reach the target, let's say, for example, the egg. And you have enough of them. And so usually the difficulty here is to understand the medium, the fluid inside. You see, and they have interactions. Now, of course, I imagine to tackle this problem, the models, type of model that you are using, are largely insufficient because you would like here, I mean, that kind of model to account also for the fluid local interactions. And so, have you looked into more physical model of interaction of micro swimmers, where, for example, you can account for the local fluids, you know, let's say the hydrodynamics? Have you looked into also this kind of question to look at, for example, how two swimmers or neighboring swimmers can, you know, depart from each other? They spend some time together, and then you look at the first time they start to diverge. Have you looked into more sophisticated model for this interaction between micro swimmers? Or no?
No.
Okay. No, because you see, I mean, they are. It's
a
complicated.
different animal. I mean, he's looking at models for building
Yeah.
consensus. There's no consensus of this. I mean, generally speaking, these
Well,
microswimmers.
Yeah. There's no general. It's not clear. It's not
Yeah,
clear.
So I had sort of similar question, but said in a slightly more mathematical way. Are all the cases you're looking at cases where there's essentially some number of flocked or states where they're all interacting together, and the system's basically moving between those various states. You're not necessarily looking at where they go into more complex states. You're basically they can be one steady state or another steady state, and then and metastable state really, and they're switching back and forth. Is that correct?
Yeah. For this model is only consider the consensus of velocities. For the vertical system, maybe it's complex. Maybe the two birds, maybe they want to keep they fly with the same velocity, but they keep a distance, to keep some distance. They also change their directions. It's very complex, but here this model is only investigate how can they get the same velocity, and another aspect for this problem we didn't consider.
I thought the Cooker-Smale had more complex states like milling and so forth. Am I mistaken?
Yeah.
If you add delay to a situation where you have oscillations,
Yeah, sure.
I mean, you make it interesting things, but it will make a much bigger difference in a problem like that than if you're just looking at going between two steady states. Yeah, then the delay will have a particular effect, but you'll basically be switching back and forth between them.
I'm guessing his first model he wrote down is like that, and that was sort of what the experiment was doing. But Cooker-Smale, I thought, allows more than that.
But I don't think you're looking at really those sort of. You're not trying to go to those states, right?
Yeah.
I don't know what the densities look like here. Can you show the sorts of densities you get for the U, for the velocity?
The density?
The PDF of V.
Yeah. Oh, sorry, V. I thought
What do you mean density?
the
Histogram.
probability density.
Oh, this for this part.
No, he should
No,
for the
for
V.
the V at the end, for the
Cooker-Smale.
Cooker-Smale.
Cooker-Smale? Oh,
Do you have anything like that figure for Cooker-Smale?
No. We only give the stability analysis for Cooker-Smale, and for this model we do some give the density, probability density for this. This is for the SPV model to describe the change of direction, and that is another model for the Cooker-Smale. It's two different models.
I understand, but I'm just trying to understand which state what ends up, which state you're in the cases you're thinking about.
Yeah, we also want to do some work on Cooker-Smale model using similar method.
Which method?
In fact, for the Cooker-Smale model, here we only do the stability analysis, and for just like the different equation has a stable point, and when the system is stable, answer this question.
Thanks.
Simple.